So in this video we're going to apply L'Hopital's rule in a case where we have the indeterminate form 1 to infinity. So the limit that we want to find is the limit as x goes to infinity of 1 plus 1 over x to the x. In Calc 1 we saw that this limit is actually Euler's number e. The form that we have, if we think about it, the form that we have going on here is, hey, the limit as x goes to infinity of 1 over x is 0 because the denominator is becoming infinitely large and we have a constant numerator. So we get 1 plus 0 is 1. So we've got a 1 sitting in here, and then the exponent x as x goes to infinity, that's x is going to infinity. So the form is 1 to infinity. And so your guess would be, if you were guessing, you'd say, hey, I think that's going to equal 1. Hey, if you raise 1 to any power, you get a 1. And so this one's actually going to defy our intuition a little bit when we work it through. So I can't apply L'Hopital's rule to this because it's not in a form, it's not a ratio, it's not a form that L'Hopital's rule can be applied to. So it's going to have some manipulation. So the technique in general, and this is going to show up in a variety of contexts, but the technique when you have something, a variable specifically, or a function in the exponent position, you want to be able to use a logarithm to get that exponent out of the exponent position. So the typical technique is to give this a name. So you just give it a letter name. So for example, we could say, hey, let y be this limit. So we get the limit as x goes to infinity of 1 plus 1 over x to the x. And then what you do to get this thing out of here is you take the natural log of both sides. So equals, you take the natural log of the left-hand side and you take the natural log of the right-hand side. So you take the natural log of the limit as x goes to infinity of the function 1 plus 1 over x to the x. And the natural log function, as long as x is on the interval, the open interval from 0 to infinity, the natural log function is continuous. So it's okay to move the limit notation out in front of the function. So I can say the limit as x goes to infinity of the natural log of the stuff that's on the interior, so the 1 plus 1 over x to the x. And then I can use log properties to take the x and pull it down out of the exponent position in front of the logarithm. So I can say equals, this is going to equal the limit as x goes to infinity of x times the natural log of the stuff, 1 plus 1 over x. And here's where we're now in a position finally to put it into a form that we can apply L'Hopital's rule to. And it's not, when you haven't seen it done before, it's not obvious that you should do it. So it's good to see somebody do it once so that it puts the idea in your head. But the idea is that we can rewrite this as a ratio. So if I put the natural log of 1 plus 1 over x in the numerator position, down here I can write 1 over x. And what you want to do is kind of quickly verify that this is the same as this. The natural log divided by 1 over x is the same as the natural log times x, which gives us back what we started with. And if I look at this and think about the form that I have, the form is going to be, hey, I'm taking the limit as x goes to infinity. So as x goes to infinity, 1 over x goes to 0. 1 plus 0 is 1, and the natural log of 1 is 0. And the denominator down here is x goes to infinity, 1 over x goes to 0. So I have the form 0 over 0. I have a ratio of two functions that has a form to which L'Hopital's rule can be applied. That means now I can take the derivative of this numerator and the derivative of this denominator. So this is going to equal the limit as x goes to infinity of the derivative of the numerator. So the derivative of the natural log, if you have crap inside the natural log function, is going to be 1 over the crap times the derivative of the crap. So it's going to be 1 over the crap, 1 plus 1 over x, 1 plus 1 over x times the derivative of the crap. The derivative of 1 is 0, so we don't need to worry about that. And the derivative of 1 over x is going to be negative 1 over x squared. So times negative 1 over x squared. If you needed to justify that, you could recognize that 1 over x is the same as x to the negative 1. So when you take the derivative, the negative 1 will pull down front. We'll subtract 1 from negative 1, which will give us negative 2. And then we can make a positive exponent by shoving x to the negative 2 down into the denominator position. So here's the derivative of the numerator over, and now we're going to do the derivative of the denominator, but the derivative of the denominator, which is 1 over x, is also going to be the negative 1 over x squared. So we get negative 1 over x squared. And then the negative 1 over x squared divided by negative 1 over x squared is going to be 1. So walking up here, what we're getting is that the natural log of y, which is where we're at now on the left, the natural log of y is equal to the limit as x goes to infinity of this divided by this is 1. And so we are left with 1 over 1 plus 1 over x. And now I can actually evaluate this, because as x goes to infinity, 1 over infinity goes to 0. I get 1 plus 0 is 1, and 1 divided by 1 is just 1. So I know that limit. And now I can dig the y out of here. I want this limit here, but I named this limit y. So once I know what y is, I know what the limit is that I'm interested in. So we do e to the natural log of y. We exponentiate both sides base e. The exponential base e and logarithm, the natural logarithm, are inverse functions. So the y drops out for us, and we get e to the first is e. So this limit, the limit as x goes to infinity, of 1 plus 1 over x to the x is equal to e, not equal to 1, which is kind of what our intuition would have thought it would resolve into.